Okay, just that it's going. Good morning, good afternoon, or good evening, everyone. Just a little quick announcement before we get started. That in January of this upcoming year, there will be a school plus a workshop in optimal point configurations on manifolds at the Erwin Schrödinger Institute in Vienna, right?
Yes.
Which we'll have will have a link posted in the chat if anyone's interested in looking into that. There we go. All right, now take it away.
Yeah, let me share again.
Okay, so today we'll have David Laat from Delft University of Technology, who will tell us about the high-dimensional sphere packing and the modular bootstrap. So David, please.
Yes, so thank you. So this is, I'm going to talk about a project that we recently finished with Nima, Henry, Thomas, Amir, and myself. And three of these, so Nima, Thomas, and Amir, they are physicists. And it's a project on basically we gathered a lot of numerical data for high-dimensional sphere packing and the related modular bootstrap problems. And then we analyzed this data in quite some detail. So in this talk, I don't necessarily want to mention everything that is in the paper, but I want to basically spend probably most of the time on really explaining the background of this and explaining this connection that is also quite recent and I think new for many of you. So if there are any questions during the talk, feel free to interrupt. I'm not sure if I can see the chat, so maybe it's better to use the microphone. Okay, so let me start with the introduction slide. So what is, so the sphere packing problem is we want to know what is the densest packing of congruent spheres in d-dimensional space. And as probably many of you know, the answer is known in dimensions 1, 2, 3, 8, and 24. So the three-dimensional case was solved by Hills. This was the Kepler conjecture. And probably this is still one of the most famous and most important computer-assisted proofs in mathematics. And then dimension 8 and 24. So there the optimal configurations are the E8 root lattice and the Leech lattice. And optimality here has been shown using the Karnaughi's linear programming band and Vyasaska's quasi-modular form. So that was a really big breakthrough a number of years ago. Basically the proof in 8 and 24 dimensions is much simpler than the proof in 3 dimensions. So this is these proofs are really much simpler. In this talk, I want to talk about high-dimensional sphere packing, and in particular, high-dimensional linear programming bounds for sphere packing. So what do we know about constructions in high dimensions? So what is the sort of the lower bound on the optimal density in high dimensions? So this is the following trick we can perform. So say we have a sphere packing in d-dimensional space in which you cannot add another sphere. So there's no space to add another sphere. Then if you double the radius of each sphere, you get a covering of Euclidean space. And well, if you double the radius of a sphere, you multiply the volume by 2 to the d. So this means that your original sphere packing before doubling must have density at least 2 to the minus d. And this is in fact still the best known lower bound up to sub-exponential factors. So whenever we are computing upper bounds, it should be sort of this shape, 2 to the minus some number times d. That is something we could. And of course, there's still an exponential gap if this. That is sort of roughly the shape we can expect of the upper bounds. So before I talk about sphere packing bounds, I want to explain this connection to the modular bootstrap. This is a problem from physics, but actually to understand it, we don't need to understand the physics, which is good because to really understand these conformal field theories, you must know quantum field theory, which is sort of a very big subject that myself, I don't know anything about. But this is not, we're not going to need this. So we can really phrase this as a purely mathematical question. So yeah, the starting point of this is that the partition functions of certain specific conformal field theories, they have the following shape. So Z as a function of tau is the sum over non-negative scalars delta d delta, which is a coefficient, and then a function chi delta of tau. And this chi delta of tau, it's defined to be the sort of the concrete function e to the 2 pi I tau delta over the data gained eta function of tau to the power 2c. So c is a parameter of our problem. And then, and that's very important, we have the following symmetry constraint that comes from this conformal. So we have z to the minus 1 over tau must be equal to z tau. So yeah, here there are already some reductions. So originally you start with a function that has modular invariance, but after some reductions, you end up with this. So we have this symmetry here. Yeah, and just some terminology. So the values of delta that appear in this sum, they are called scaling dimensions. And the smallest non-zero scaling dimension is called the spectral gap. And then the question is, or one sort of important question here is, how large can the spectral gap be? Yeah, and so just to further clarify this, so the parameter here is c. So for each value of c, we have a problem that we want to solve, and the variables are the scaling dimensions delta 0, delta 1, delta 2, etc. And these coefficients, which are called degeneracies. And then the first scaling, so the zeroth scaling dimension is 0, so 0 always appears in the sum. And the first the zeroth non-degeneracy is equal to 1. Yeah, and so this already sort of has a similar flavor as sphere packing, because well, in sphere packing we have a problem for each dimension d, where we have a problem for each scalar c, and also this sort of asking how big the spectral gap can be, that we can relate it to the question what can be the radius of the spheres in the sphere packing. But I'll make this more clear later. Okay, so how can we relate this to sphere packing? So the idea is that we're gonna derive, well, this has been done before, right? This is not our work, but I want to show you the derivation of the linear programming bound for this problem. And then I will show you that this linear programming bound is actually the same as the linear programming bound for sphere packing. So, so how can we compute the upper bounds on this spectral gap? So it starts with the following definition. So we define this function by taking the difference of these two functions. And then we get a crossing equation. And this really follows immediately from, so let me show it. This follows immediately from the symmetry condition and this definition of the partition function. So this immediately gives you, if you sum this function here with the degeneracies as the coefficients, you must get 0. And then given a delta gap, some number greater than 0, and we define a linear functional that is strictly positive on the zeroth, so on phi sub 0, and that is non-negative on phi sub delta whenever delta is at least delta gap. And applying this linear functional omega to the crossing equation, well, gives you 0, simply because the crossing equation is 0, right? So omega of this thing is also 0. But then we can separate the first term from the series. So we get omega of phi 0 plus all the other terms. So if this is strictly greater than 0, the first term, and if all the terms here are, and if you have to get 0, then one of these terms here must be negative. But these values are all non-negative. So that means that there must be a term here where delta is smaller than delta gap, right? So this omega proves an upper bound delta gap on the first scaling dimension, on the spectral gap. right? So, and if you know linear programming bounds, then you probably realize that this really has the same flavor as linear programming bounds for these kind of geometric problem for sphere packing and similar geometric problems. But I want to make this more precise, even this connection. So, so what Hartman, Mazak, and Rastelli did, they formulated this problem I showed on the previous slide as an uncertainty principle. So what they did is they wrote this optimization problem. So basically, you get an optimization problem where you try different values of delta gap, and for each try to find such an omega. So they formulated this optimization problem as an optimization problem over functions f from r to the 2c to r that are not identically zero, and well, which are an eigenfunction for the Fourier transform if eigenvalue -1, and which have the following inequality constraints. So f of x is non-negative whenever the norm of x is at least this number here. So, and sort of why is this equivalent? So one direction follows. So if you have such a linear functional that I displayed on the previous slide, you can use it to define a function f, and this function f will satisfy these constraints. And then you can show that you can construct a basis, and you get essentially all those functions. So it's really an if and only. So this problem is really identical. So this type of uncertainty principles was introduced by Bergen, Klosel, and Kahan, and also recently studied by Cohen and Gonsalves in the connection to the sphere packing problem also. So, but yeah, now we're not really, not yet at really the linear programming bound for sphere packing as it is usually stated. So let me show you the final step also. So the Kanelkis bound is the following theorem. So given a function h from Rd to R that's integrable, continuous, and has a radial and has an integrable Fourier transform, and given a positive real number R. So if these three conditions are satisfied, so here we have normalization conditions, we have a similar inequality condition than shown on the previous slides, and then the Fourier transform has to be non-negative. So if you have such an auxiliary function h, then every sphere packing m r to the d has density at most, well, some constant, the volume of a sphere of radius r of 2, or the volume of a sphere of radius r over 2, right? So why is this equivalence? So one direction is easy. So if h is a function that satisfies the above conditions, then we can construct f like this, f is h hat minus h. And this satisfies the conditions on the previous slide, where you set c equal to d over 2. Right, so you have that, then it's immediate that f hat is minus f. And since h hat is non-negative everywhere, and h is non-positive outside of this ball of radius r, you also get that f of x is non-negative outside of this ball. So this direction is easy. So the other direction is actually an open question, but there's a lot of numerical evidence for the other direction. So the other direction probably is not easy at all. Okay, so this is the connection to this problem in physics and the linear programming bound for sphere packing. So we don't really know whether these conformal bootstrap problems are also really connected to sphere packings themselves, but at least there's this very interesting connection between this linear programming bound and these conformal field theories. Okay, so this is the connection. So now I want to go to how can we use this linear programming bound to do computations. Okay, so my clock disappeared, so let me just, okay. So, we're gonna sort of change notation a bit here, and we are gonna consider f now as a function of delta, where delta is the norm of x squared over 2. And then what can we do? So we want f to be an eigenfunction for the Fourier transform with eigenvalue -1. So how can we make sure that that's going to be true for the functions we're going to optimize over? So what can we do? We can look at these functions fk, which are defined by a Laguerre polynomial times, well, times a Gaussian, if you think of this as a function in terms of x. And well, this is a Laguerre polynomial with this parameters, c minus 1 and degree 2k minus 1. And that means that these fk's as a function of x are eigenfunctions of the Fourier transform with eigenvalue minus 1. So if you define f like this as a linear combination, where the alpha k's are free variables, can be positive or negative, it's automatically, it's guaranteed that f will be an eigenfunction for the Fourier transform with eigenvalue minus 1. Right, so that sort of makes sure that one half of the constraints are always satisfied. And then for the other half, we have the inequality constraint outside of this ball. So checking whether f satisfies the inequality constraint. So this is a semi-definite program. So this we can do on a computer. The problem is that this is computationally very expensive for large n. And that is sort of a common theme in these kind of problems. So semi-definite programming is a really powerful, well, say language to model problems in. But very often, if you have a specific problem you care about, it helps to sort of look for more specialized algorithms. So, and that's also what is happening here. So why is this a problem that is computationally expensive for large n? So to get good bounds in high dimensions, we need large n. Okay, so numerical optimization. So instead of using semi-definite programming, we can do something else. And so we can fix delta 1, and then we can maximize f0. So that's just to make sure that f is not going to be identically 0. So we can maximize f0 over these coefficients alpha k, but now also over delta n, subject to the following constraint. So we say that f of delta 1 must be 0, and then we want double roots on all the other. So what is going to happen here is that we're going to have a single root at delta 1, and we're going to have double roots at all the other deltas. And that means that our function is going to be non-negative or non-positive, whatever you want, beyond this value delta 1. Right? So this is a sort of a, another way of certifying that this function has the right, of making sure that this function has the right signs. And then if this f of 0 is indeed non-zero, that means f is not identically 0, and then delta 1 will be an upper bound on the spectral gap. So for sphere packing, this approach was used by Kohn and Elkies in the original paper where they introduced this Kohn-Elkies bound. And in the conformal bootstrap literature, a similar approach was used by Alciak and Paulas. So recently, so the co-authors from physics, also in this project, they improved this method by dualizing the optimization problem we have here by dualizing this problem. But if you dualize this problem, so this is a convex optimization problem. So normally, if you would dualize this, you have these infinitely many constraints here, which means you would expect that the dual variable is going to be something like a measure, a distribution on this infinite interval, right? But using this alternative shape of the optimization problem, they realized that actually this dual measure only needs to have finite support, and indeed it's a sum of just n direct point measures. So in the dual we get these equations. So so if let me just show you this sum. So here we have 2n. So we truncate here to have 2n terms, and that corresponds to needing in the dual n of these direct point measures. So these are the constraints we get. And then, well, performing some small trick, these become 2n polynomial equations in 2n variables. And this also turns out that you can solve this efficiently by Newton's method. And then one tricky aspect of using Newton's method is you need really good starting points. And what they did is they used a solution or solutions for smaller values of n to predict an approximate solution for larger values of n, and use that as a starting point for Newton's method. And this works really well in practice. Okay, so we use this to gather a lot of data and to get a new we can extrapolate this to get to predict the asymptotic for the linear programming bound for sphere packing. But before I show that, I want to also I want to compare that, well, 1 to the lower bound is 2 to the minus d, but also to the best known asymptotic bound that we know, and that is the Kapuscinski-Levenshtein bound. So I want to really quickly show you how this analytic construction works. So here's just so here I want to go really fast. So the only thing we do here is we define a number of orthogonal polynomials. So, and if A and B, they are parameters, if they are 0, then these are just the Gegenbauer polynomials, or the ultraspherical polynomials. And we also want to look at these for A is 1 and B is 1. And then these are Jacobi polynomials in general. So why do we use this weight function here? This sort of complicated expression. So why do we want them to be orthogonal for that weight? So that, well, can be explained as follows. So if we consider a continuous function on this interval, and we integrate this continuous function with this weight function, now with 0, 0 here, then that is exactly the same as viewing this function on the interval as a function on the sphere in the following sense. So we take a point x on the sphere, take the dot product of an arbitrary fixed point e, and then evaluate the function at that. So this is a zonal function, a rotation invariant function on the sphere, this f here. And then if you integrate it over the sphere, that's where this weight comes from, right? So this probably for many of you, this will be very familiar. And this means that we can see these orthogonal polynomials, these polynomials as orthogonal zonal functions on this d-dimensional sphere. Well, then we have the addition formula, and this, well, tells us that, well, actually, so, well, from that we can deduce that these type of functions are of positive type. So what does that mean? Oh, there's still a bug in here. This should be the dot product between x and y. So these matrices you can form in this way. They are positive semi-definite matrices. Okay, so, and then Schoenberg also tells you that these are essentially all positive type functions. So any continuous function that is positive type, you can write it as a uniformly converging series of these polynomials. Okay, so now I want to go to the compact analog of the Kornelkis bound, or actually this is all older, of course, than the Kornelkis bound. And what can we do here? So if you define ADS to be the greatest cardinality over all sets, subsets of the unit sphere, where the dot products are in this interval -1s for all distinct x and y in the code. So then this is sort of the analog of the optimal sphere packing density, right? The compact analog of that. Then the del Sartre-Gödel-Seidel bound says that if you take a function, a continuous function on this unit interval, that is of positive type as a zonal function on the d-dimensional, or on the d-1 dimensional sphere, so the sphere in R to the d, and satisfies this inequality, then we can upper bound this cardinality by this expression f of 1 over f naught. So this is very similar shape to the Kornelkis bound. And well, what we did on the previous slide, that shows you that you can actually approximate these functions. So it's an optimal function by non-negative linear combinations of these Gegenbauer polynomials. And then, well, you can use that to use linear programming or semi-definite programming to actually numerically compute this bound. But what Levenshtein did instead, he analytically constructed very good feasible solutions to the del Sartre-Gödel-Seidel bound. So yeah, I want to briefly show this. So this is fairly old, but still I want to briefly show you because I think it's also very nice. So we define these roots of these polynomials. And then for the degree 0 polynomial, we just set this root to -1. And then you can show these inequalities. So this divides the -1, 1 interval into subintervals between these two numbers all the time. And then the auxiliary functions for the del-Z-Codelcidal bound that Levenstein constructs, well, they're sort of complicated, but they're very concrete, right? They have the following shape. So for each, depending on the value of S, and S, let me recall, S is here the cosine of the angle that we are interested in here. So for each value of S, we get a function. And the claim is that this function is actually feasible for all the constraints in the del-Z-Codelcidal band. And well, what's the shape? So for instance, if we look here, this is t minus s times a square. So the inequality constraint, so let me go back. This inequality constraint is immediately satisfied just by the shape of this, these functions. So the only thing we have to worry about is this function actually of positive type, right? That's the other condition. So, and that actually, that I think is really beautiful. So that follows from using a Christoffel-Darboux formula. So whenever you have orthogonal polynomials, like these polynomials here, these qi10, you can, you have a Christoffel-Darboux formula that is the following shape. So t minus s times this sum can be expanded like this. Or normally this t minus s is written here in the denominator. And okay, so now we're not immediately done. There's some more work. So I will go sort of explain really quickly how this works. So these functions qi10 of t, they are positive type as function of t. And these values here, you can show for the right s, when s is in this interval, you can show, so s and k, they have to match. Then you can show that these values are non-negative. So this is a non-negative linear combination of positive type functions, which means that this k is of positive type. So, and then here, something similar happens. So this is a positive type function of t. This number is positive. This is a negative number. And this is again a positive type function. So this whole thing is positive type. Which shows you that this thing here is of positive type. And then you can show that the pointwise product of positive type functions is of positive type. And that shows you that this is of positive type when S and K match, when this condition is satisfied. So I think this is really, really a nice construction. That's basically why I wanted to show you this. So this is for spherical codes. And now I want to go back to sphere packing. So for this, we can use the following geometric inequality. So the sphere packing density in d-dimensional Euclidean space is at most the following expression. So we can minimize this factor times this optimal cardinality of the spherical code. So, and then if you combine this with the Kapuscinski-Levenstein bound is obtained by combining the universal bound on the previous slide, or actually originally is slightly weaker, but it's not so important, with the above geometric inequality. This gives you the best known asymptotic sphere packing upper bound. So, and as you can see, this indeed has sort of the same shape as the 2 to the minus d. That's the best known lower bound up to sub-exponential factors. And of course, this means there's an exponential gap, right? But at least it has sort of the same shape. Okay, so now I talked about how can we compute the Cone-Elkies bound numerically. And we did that in high dimensions. And what is the best known analytic and in fact, the best known bound in general in very high dimensions. So here's a plot comparing these two bounds. So we have the Kapuscinski-Levenstein bound here. So on the vertical axis is the logarithm of the density over the dimension, just to get a nice plot. The black line is the linear programming bound as we computed it numerically. And of course, this might look like they actually converge, but then if you extrapolate both of them, it's showed here. By the way, I'm assuming the whole talk that you can actually see my mouse pointer. Okay, that's true. Very good. So, so here we extrapolate, and this shows that they're probably not the same. So to make that a bit, so here I want to go into a bit more details. So here we can see this more clearly, what is going on. So here on the first column we have the dimension. The second column, so this is the exponent. So you should think of, for instance, dimension 256. The linear programming bound gives the density upper bound of 2 to the this number times d, right? And then Kabushansky-Levenshtein, if you compute the optimal one for that dimension, you would get this number. And then if you look at this, then the question is, does this go to 0 or not, right? So if we want to answer the question whether this goes to 0 or not, we want to look at the differences between consecutive numbers here. And then the question is, does this go to 0 sufficiently fast, right? So if this goes to 0 very quickly, then this will not go to 0, right? So how can we, so what can we say about this? How quickly does it go to 0? So to say something about that, we look at the ratios of consecutive numbers. So in the beginning, it's not so interesting, or that's sort of not so interesting, but then what happens here, it seems to be steadily growing, right? So, and our extrapolation is based on only one assumption, and that is that this number here will never drop below 1.92. So that's the assumption we make in our extrapolation. And then if you do that, so you can just compute, so if given that assumption, what happens to all these numbers? And then we get the following conjecture, and that is that the Kanauki's bound proves the following upper bound. The sphere packing density is at most this number, where lambda is some number between 0.604 and 0.605. Okay, so this is one conjecture, and then another conjecture is that actually this constant, this optimal constant lambda, is the following number. And here this might look a little bit silly because, well, we only have a few digits here, and this is a sort of a symbolic expression. Well, you could think of making up many symbolic expressions that have sort of similar complexity. But then if you look at this from a different angle, from a different perspective, then so this A minus D, I didn't explicitly define it, but this is the in the uncertainty principle that I showed in the beginning. This is this minimal radius for which you can get this non-negativity outside the ball of this radius. And this grows roughly as root d. So if you look at this limit, this goes to a number. And this conjecture is equivalent to saying that this number is 1 over pi, which is sort of much more reasonable. But of course, yeah, the first conjecture I think we have a stronger belief in the first conjecture than this one, but this would of course be very nice if this were true. Okay, so that is so in the paper so as I said, we gather numerical data in high dimensions, and then so the whole paper is about analyzing this numerical data in many different ways. So in this talk, I don't have time to go into all of this because I also really wanted to explain sort of the background of this. But there's one other thing I want to show you, and this has to do with implied kissing numbers. So suppose H is an optimal function for the Kanauki's bound. Then by a scaling argument in a paper with Cohn and Miller, the average kissing number of any sphere packing that would attain the Kanauki's bound must be equal to this number. So so remember the function is going down at R. So H prime of R is a positive number. So this is a positive number. And the average kissing number of any packing attaining the bound for this optimal function H must be equal to this number. And we call this the implied kissing number of the bound. Yeah, and then we can, okay, again, look at some numbers. So here it's again the density bounds. You might recognize these numbers now. And this is the implied kissing number. Also, I'll log 2 over d of the implied kissing number. And then if you look at these numbers, you see, okay, if I add these two numbers, this goes to 0 basically. Or if I add the absolute value of this onto this one, it goes to 1 basically, right? That is shown here in the last column. So, and what I really like about this connection between geometry, the sphere packing problem, and this modular bootstrap that has been discovered recently, is that we can now use techniques that physicists use a lot to sort of say something about this. So again, very briefly want to show you what we can say here. So the modular invariance of the partition function. So this invariance I showed you on one of the first slides. So this with a very easy argument gives you this expression. So if we sum these degeneracies with this factor here, then this is roughly 2 pi over beta to the power c. And then using a Tauberian theorem that physicists use a lot in their research, we can say something about the partial sums of this if you remove this factor. So this is called an abelian summation with this factor in there. If we remove it, using a Tauberian theorem, we can say something about these partial sums, and they look like this. So the integral of some function that is here, you don't have to really know what this is, but there's some function so that this partial sums are the integral of that function as I go to infinity, as I goes to infinity. And using this expression here, we can say something about, so I haven't used this notation before, but think of optimizing the linear programming band. So that gives you the scaling dimensions and the degeneracies. And this D1 LP, this is the first degeneracy. And then if you look at this expression, so then the first scaling dimension here in this sum, so D1, has to be roughly equal to the integrand here multiplied by the width between peaks. So this is the height here, and this is roughly the width. Of course, why do we take delta 2 minus delta 1 as the width and not, for instance, delta 1? So that's basically because numerically this works out nicely. So this is not a formal proof. I'm just showing an argument that sort of gives us a better understanding of this numerical behavior. And then, well, this factor here is sublinear in C. In fact, delta 1 is roughly linear in C. So if you go to very high scaling dimensions, so say delta 1000 minus delta 999, that will be roughly 1. And well, that means that so this delta 2 minus delta 1, it seems to be close to root C actually. And this implies that the implied kissing number is actually 2 to the d times the Kornelki's bound, which is exactly the behavior you see here. So yeah, as I said, this is not, it's not a proof or anything, but it sort of gives us an understanding of this numerical behavior. And I think that's sort of a very nice result of this connection to the modular bootstrap, so that we sort of can also use those techniques in this setting. Okay, so with these implied kissing numbers, so we also show that, so in a paper together with Olivier and Valentin, we showed that you can sometimes improve on the Kornelki's bound if you have a bound on the average kissing number. Well, basically, what we did is we used a good bound on the average kissing number, and then we ran some computations that showed in some fixed dimensions a better sphere packing upper bound than the Kornelki's bound. So what we show in this paper is that whenever you have an upper bound on the average kissing number that is better than the implied kissing number, then you can always improve the Kornelki's bound. And then it's a very sort of natural question. So to define the Kapuscinski-Levenshtein bound, we used first spherical codes, right? So auxiliary functions for the Delsart-Cadel-Seidel bound. and then this geometric inequality that I showed you. But actually you can use, so you can also, that's done in a paper by Cohn and Zhou, you can transform your auxiliary function for the Gödel's saddle band into a feasible function for the Konokis band. So the Kapuscinski-Levenshtein band is at least as strong as the Konokis band. But now so sort of a very natural question is, could we perhaps again use spherical codes? So could it be that the upper bounds on the average kissing number that we can obtain with this Del-Side-Gödel saddle band can be used to improve on the Konokis band in all dimensions except, of course, these dimensions where the band is sharp. Yeah, and in this plot we show that the answer is no. So this is the ratio of the implied kissing number to the Del-Side-Gödel saddle kissing number upper bound. And then you see, okay, in 2, 8, and 24 dimensions, these numbers must be equal, which is indeed what happens. And then for many dimensions, the kissing number band is better, which means you can improve on the Konokis band. But then it starts to sort of, here in 2 dimensions it goes below, and then here it also goes below, and we don't really know what happens asymptotically. We don't really, from this plot, we cannot really state a conjecture what happens asymptotically. So I think that's also very interesting, this behavior. Of course, it would have been very nice if in some dimension it would again match exactly, because that would sort of suggest that there's another really interesting sphere packing, but that's also unfortunately doesn't happen. Yeah, so finally, the final thing I want to say is that we also show that the implied kissing number is actually an upper bound on the average kissing number of any sphere packing. And that means that, so if you solve the Konokis band in a given dimension, so either the implied kissing number is bad, and that means that you can use a better upper bound on the average kissing number to improve the Konokis band, or it is actually the best known upper bound on the average kissing number. So I think that's also of interest. Okay, so that's everything I wanted to say. Thank you for your attention.
Great, thank you very much. This is super exciting. Are there any questions? Okay, so while people are thinking about their questions, I mean, so sort of without even thinking about making this any of this analytic, do you think it would be feasible to take some of these numerical results and make them precise as you do in your other projects?
So you mean this exact bounds paper with Philippe? Yeah. So there, the situation is that we only consider bounds for compact problems. And if you consider a compact problem, I don't think there's a proof. But in practice, what we see is that in your expansion of your function, so you always expand your function in terms of, say, Gegenbauer polynomials, or in this case, Laguerre polynomials times Gaussians. So in your expansion, you only need finitely many terms to get a sharp bound. So then we get numerically really a sharp bound, and we can round that to an exact bound. So here the situation is different. So here in our expansion, and that seems to be sort of happening in a compact setting, you need infinitely many terms. And the reason for that is that we model our functions as polynomials times Gaussians, but we actually know from complementary slackness that there must be infinitely many zeros. So we know that for any finite degree, we cannot actually get a sharp bound. So that I think makes it impossible to use this rounding technique we have. And that's also why Marina really needed to construct a function, not as a polynomial times a Gaussian.
Yeah, okay, I see. Okay, let's see. We check the chat.
Are there,
Questions? Yeah.
so you were talking a bit about methodologies involving things that physicists do that just kind of piqued my curiosity and made me wonder, this is just something I don't know. Do physicists have a reason to be interested in the kissing numbers or spherical packing in dimensions higher than 3?
Yeah, that's a really good question. So I think, so now they're interested in sphere packing, I think just for the reason that the linear programming method for sphere packing turns out to be exactly the same as the linear programming bound they have for their problem of bounding the spectral gap. So I think that's really where this interest right now comes from. But as I said, right now, I think we don't know if there are deeper connections between sphere packing and conformal field theories. So, and also, for instance, spherical codes. So in the interest presentation, I mentioned how we can use bounds for spherical codes to improve the Konelkis band. Mm-hmm. So right now, it's not really known whether this could also be of use to do something for CFTs. So yeah, right now we did. So in this paper we didn't, but yeah, I don't know if something can be done there. But so the high dimensions the reason there. So high dimensions in sphere packing corresponds to a high value of C in their setting. So they're always conformal field theories in dimension 2. But it just means that, yeah, you're varying this parameter. You're going to a high energy domain. But I shouldn't say too much about that because I really don't know anything about the physics behind this.
Okay.
So, but this high dimension for us is not high dimension for them. It's something else. It's high energy, I think.
Okay.
Yeah, so this graph, okay, before we ask for more questions, so this graph you have on the previous slide, yeah, the previous slide, yeah. So this is very very strange, right? So it feels like you have at least, so you have so many different regimes. So some places where, you know, Kapotensky-Levenshtein beats Konelkis, and then so yeah, it's very. So do you expect there are other flips? Like you expect further to the right, it goes up above the one line, or what does it do? Does it stay below?
No, yeah, from this plot, I really don't dare to make a prediction. So one thing you could, with a bit of fantasy, see is that it's sort of a periodic behavior like this, like 3 ways. But yeah, I really don't know if that is. So yeah, I think we really would need more data to be able to say. So this is not related to Kapotensky-Levenshtein. This is really about whether the Del-Saddle band on the average kissing number can strengthen the Konelkis band, right? And then in these dimensions it can, but when it drops below 1, it can't.
Yeah. Right. Yeah. Okay. Okay. We have question from Henry. It's a comment from Henry. Okay, so Henry says in physics terms, dimension divided by 2 is central charge, aka the number of bosons. So high dimensional sphere packing corresponds to a large number of particles. Right. Okay. So to physicists, higher dimensions mean more particles.
Yeah, so I didn't really specify in the beginning what kind of conformal field theories, but they're all 2-dimensional in this setting. So yeah.
Yeah, so it's fascinating because this also has this what was it called? A partition function, I think.
Yes.
This also has some modular properties.
Yes, exactly. Yeah.
So that's
Yeah. In fact, so here it has just one of these symmetries, right, for one of the generators.
Yep.
Of,
Yep.
SL2Z. So that's actually reduction. So you start off with a different partition function in two variables. That is the full symmetry.
That has
there's
both.
reduction.
Okay.
Yeah. So, but yeah, basically, I wanted to start off of the simplest concrete problem.
Cool. Yeah, this is very very cool actually.
Yeah, and as I said, we analyze a lot of the numerical data in the paper that I didn't talk about here. That's basically because I wanted to sort of sketch the background. So if you want to see more plots, download the paper.
Let's see. Do we have any questions in the chat? Yeah. So please go ahead and ask questions. I'm sure there are many questions.
I mean, maybe I can stop recording now then,
Okay.
if that makes a difference to anyone.
Okay. Yeah, sure.